We think we know what a black hole is, a place where time stops at its edge, where nothing, not even light, can escape, a cosmic monster that swallows everything without mercy. But here's the problem. Almost every part of that picture is incomplete. Black holes weren't discovered through telescopes. They were born on paper, as equations that refused to be ignored. And ever since, something strange has happened. Not in the mathematics, but in the language we use to explain it. This video isn't about fear or spectacle. It's about how familiar ideas quietly mislead us, and why, decades later, we still don't really understand black holes. Before we begin, thank you for being here. If you feel connected to this space, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. Before we ever saw one, before a telescope ever hinted at one, black holes existed as ink, not as objects in the sky, not as monsters hidden in galaxies, but as a consequence of a set of sentences written in mathematics, sentences that Albert Einstein finished placing into their final form in late November of 1915. And this is where the story begins to feel unsettling, because when something appears first in an equation, it does not arrive with photographs. It arrives without texture, without sound, without a clear boundary between what is real and what is merely permitted on paper. And when the universe offers us a possibility that extreme, our first instinct is not understanding. It's mythology. But then, the mathematics refuses to let go. On November 25, 1915, Einstein published the field equations that sit at the heart of general relativity. Those equations didn't just adjust gravity. They replaced the old idea of gravity as a pulling force with something colder, stranger, and more precise. Mass and energy tell space-time how to curve, and curved space-time tells matter, and even light, how to move. That single shift is why black holes could be born in theory before they were born in observation. Because general relativity doesn't ask what we expect to happen. It asks what must happen if the equations are taken seriously. And when you take them seriously, you encounter something like a trapdoor hidden in the structure of reality. Not a trapdoor made of metal, a trapdoor made of geometry. Just weeks after Einstein's equations were released into the world, a German physicist named Carl Schwarzschild, working during World War I, found an exact solution. It was submitted in January of 1916. Schwarzschild wasn't describing a real object anyone had detected. He was answering a mathematical question. If you have a perfectly spherical mass, what does space-time look like around it? And his solution did something disturbing. It hinted at a boundary, a place where the math seemed to misbehave, where certain quantities blew up, where the description looked as if space-time itself was tearing. For years, that boundary was treated like an embarrassment, a singularity in the equations, a sign that something had gone wrong. And this was the first fracture in the human relationship with black holes. We saw a mathematical inevitability, and we mistook it for a physical certainty. Or, just as dangerously, we saw a mathematical difficulty, and we mistook it for proof that nature would never allow it. Either way, misunderstanding arrived before the object did, because at that time, the sky was silent. There were no X-ray telescopes, no radio arrays, no gravitational wave detectors, no way to point at a region of space and say, there, that is one. So black holes became, in the public imagination, something like ghosts of mathematics. And ghosts are easy to exaggerate, easy to fear, easy to turn into something supernatural. But inside physics, something else happened. A second path opened, a path not about static solutions, but about collapse. In 1939, J. Robert Oppenheimer and Hartland Snyder published a paper in Physical Review describing what happens when a sufficiently massive star runs out of the energy sources that hold it up. They studied an idealized collapse, Simplified, yes, but mathematically sharp. And what they showed was chilling. For the matter falling inward, the collapse can complete in a finite amount of time. It doesn't almost happen, it happens. But then, an observer far away sees something different. From far away, the collapsing object seems to slow as it approaches that boundary. To the distant eye, it never quite finishes. And right here, a very human confusion takes root. We want one story, one clock, one clean sequence. But general relativity offers multiple viewpoints that are all true at once, each locked to its own experience of time. And without careful language, we turned that subtlety into a myth. We began to speak as if the universe itself was playing tricks, as if time stops, as if reality freezes. But that is not what the physics demands. It's what our instincts demand. Because we do not naturally think in curved space-time. We think in stories with simple endings. Now, notice the strange tension forming. For decades, black holes were not an observed category of nature. They were a debated consequence of theory, a possibility that mathematicians could not ignore, and an object that astronomers could not yet touch. And whenever theory runs ahead of evidence, our language becomes dangerously powerful. Because language fills the gap. It pours concrete into the empty spaces, and once it hardens, it becomes difficult to break, even when the science matures, even when the evidence arrives. But the evidence did arrive, not as a dramatic picture at first, not as a perfect silhouette. It arrived as a wound in the sky, a source of invisible violence. In 1964, a sounding rocket detected powerful X-rays coming from the constellation Cygnus. That source became known as Cygnus X1, and NASA describes it in a way that matters for our story. It was the first cosmic object ever identified as containing a black hole. That's not seen, not the way we see a planet or a nebula. It's identified, inferred, cornered by evidence, and even then it took time for confidence to crystallize across the scientific community. Because this is what born from equations really means. The first black holes we met were not photographed. They were argued into existence. They were accepted the way a jury accepts a verdict, through converging lines of testimony. And that means the public didn't inherit black holes as careful scientific objects. The public inherited them as already mythologized characters. By then, even the name had arrived. In 1967, the term black hole entered the culture of physics, popularized by John Archibald Wheeler. And the name is brilliant, but the name is also a trap, because it sounds like a thing, a hole, a tunnel, a pit, a mouth, a place that sucks, a place that swallows, a place that behaves like a vacuum cleaner aimed at the universe. And once that image takes hold, everything that follows becomes harder to explain. Because we stop thinking of black holes as regions of space-time, and start thinking of them as cosmic objects with intentions, as predators, as monsters, as hungry darkness. But black holes are not born from hunger, they are born from geometry, and that distinction matters more than almost anything else we will face. Imagine this, you're standing in a city at night and someone hands you a street map, but it's not a photograph, it's not a satellite image, it's a set of rules. Straight roads must stay straight, intersections must meet at right angles, distances must follow the grid. Now imagine the rules, demand something extreme, a sharp bend in the grid that forces every street nearby to point inward. You haven't seen the city, you haven't walked the streets, but the logic of the map says that bend must exist if the rules are true. That is what Schwarzschild's solution felt like to early relativity. A bend demanded by the rules, but without a city beneath it yet, and that gap between rules and reality is where misunderstanding breeds. So why did theory come first? Because general relativity is a machine that produces consequences. Once you accept Einstein's equations, They do not politely stop at familiar outcomes. They push into extreme regimes, places no human senses evolved to imagine. And for decades, the evidence simply couldn't keep up. Astronomy in the early 20th century could not easily see X-rays from space. Earth's atmosphere blocks them, so the sky could host violent, high-energy phenomena, and we would never know. Only when rockets and space-based instruments arrived could we begin to detect the indirect fingerprints of compact objects, bright X-ray sources, orbital motions, energetic accretion flows. But even after we had candidates, we still had to fight our own language, because the earliest descriptions were built for mathematicians, not for human imagination. Singularity, gravitational radius, completely collapsed object. Then the language became cinematic. Black hole. And cinema is not neutral. The phrase doesn't just label, it suggests. It implies a surface, like a pit. It implies empty space inside, like a tunnel. It implies suction. It implies destruction. And the universe does not care what the words imply. The universe cares what causality allows, what space-time permits. And this is the danger we must name clearly. A mathematical result can be inevitable, and still not tell us how to picture it. A mathematical solution can be consistent and still be misunderstood by every metaphor we use. The misunderstanding isn't because the public is unintelligent, it's because black holes force us to speak about reality using language built for everyday life. And everyday life does not include horizons of no return. Everyday life does not include the bending of time. Everyday life does not include a place where the future points inward. But then, once we admit that black holes were born as equations, we have to face the deeper discomfort. If they were born from equations, then our first images of them were not shaped by nature. They were shaped by us, by our metaphors, by our instincts, by the way we talk when we don't yet fully understand. And now, a quiet question opens beneath our feet. If black holes entered human thought as mathematics first, then what else did we inherit along with them? What assumptions did we smuggle in without noticing, just because the words felt intuitive? Because the next step is where gravity stops behaving like anything we grew up believing. Not because it becomes stronger, but because, near extreme mass densities, gravity stops being intuitive at all. And once our intuition breaks, the real misunderstandings begin. Gravity feels like the most dependable thing in our lives. We drop a coin, and it obeys. We stand still, and the ground holds us. We build cities because we trust that down will remain down. But then, we move closer to the heaviest places in the universe, and gravity stops behaving like a force we can picture. It stops feeling like a pull. It becomes something colder, something geometric. And that is where our understanding begins to fracture, because our instincts were trained on Earth, inside mild gravity, inside slow motion, inside a universe that rarely bends hard enough to betray its true shape. But near extreme mass densities, gravity doesn't just get stronger, it becomes different. And the first mistake we make is subtle. We keep talking about gravity as if it reaches out like a hand, when, in Einstein's universe, gravity is often what happens when the hand is no longer there. For centuries we described gravity the way Isaac Newton made it usable, a force between masses, invisible, but direct. And it works beautifully for most of human life. It can tell us why apples fall, why planets orbit, why the moon holds the oceans in a slow rhythm of tides. But general relativity steps in and quietly changes the category. It does not treat gravity as a force that acts through space. It treats gravity as the shape of space-time itself, warped by mass and energy. And if that sounds abstract, there's a reason. Our senses didn't evolve to detect curvature in space-time. We evolved to detect slopes, edges, impacts, winds, things you can touch. Space-time is not something you can touch, yet it can steer everything you will ever touch. And this is why black holes confuse us so easily. They don't just intensify gravity, they reveal what gravity truly is. When the curvature becomes so steep that everyday metaphors begin to lie. A good metaphor should clarify, but most of the famous gravity metaphors quietly sabotage the truth. The rubber sheet image, space as a stretched fabric with a bowling ball sinking into it, seems helpful, except it smuggles in the very idea we're trying to escape. It makes gravity look like a downward pull caused by something sinking. It makes space-time look like it needs an external down to work. But the real universe has no outside floor, no cosmic table, no external direction that space-time sinks into. That metaphor can be a doorway, and then it becomes a trap, because in general relativity, objects don't fall because they're being pulled in the way we imagine. In the simplest sense, they fall because they are following the straightest possible paths available in curved space-time, paths the geometry itself has reshaped. And here's where everything cracks open. If you are freely falling, you are not feeling gravity. You are weightless. Einstein captured this with the equivalence principle, a deceptively simple idea that says you cannot locally tell the difference between being in free fall in a gravitational field and drifting weightless in deep space, because in a small enough region the physics looks the same. So the sensation we call gravity on Earth, this constant heaviness, doesn't come from gravity pulling you. It comes from the ground stopping you from following your natural freefall path. That is not poetic phrasing. That is the core reversal. Gravity, in Einstein's view, is often what you don't feel, and once we accept that, we have to accept something even more unsettling. If gravity is geometry, then strong gravity isn't just more force, it's more distortion. It's space-time bending so intensely that what counts as straight becomes unrecognizable to human intuition, and that is why black holes feel like paradox machines. Because black holes are not, at first, about crushing strength. They are about extreme curvature, so extreme that the universe's usual rules of common sense stop being reliable. But then, a new problem appears. If gravity is not a pull, why do tides exist? Why do objects stretch and break near black holes? Why does anything get torn apart at all? The answer is hidden in something Newton could describe, and Einstein could deepen. Gravity is not uniform. It changes across distance. A tidal force is simply the difference in gravity between two nearby points, like the moon pulling slightly more on Earth's near side than its far side, raising tides. Near a black hole, that difference can become catastrophic, not because gravity is grabbing you, but because the geometry is varying so sharply from place to place that different parts of an object are being guided along different natural paths, and the object cannot stay intact while trying to obey two different straight lines at once. NASA explains tidal forces exactly in this spirit. They are differences in gravitational strength across an object, and if those differences exceed what holds the object together, disruption follows. So when people imagine a black hole as a kind of cosmic vacuum, the reality is stranger. It is not sucking, it is shaping, it is sculpting the allowed directions of motion, and when the sculpture becomes steep enough, the result looks like violence, stretching, compression, fracture. Not because space-time is angry, but because it is indifferent. And here's the strange part, even light obeys this geometry. In 1919, astronomers used a total solar eclipse to measure the deflection of starlight passing near the sun, an early historic test of general relativity. Light doesn't have mass, so a Newton-style pull is not the right intuition. Yet the path of light still bends in curved space-time, because the geometry is bent. That eclipse wasn't just a scientific victory, it was a warning. It told us the universe does not require objects to be heavy in order to be guided by gravity. It only requires them to exist inside space-time, and black holes are what space-time looks like when that guidance becomes extreme, which is why our everyday intuition collapses. Because everyday intuition says forces push and pull. But black holes are not primarily a story of pushing and pulling. They are a story of allowed paths narrowing and narrowing until the geometry itself decides what forward even means. Imagine this. You're walking through a crowded hallway in a school. Most days the hallway is wide. You can move freely. You choose your direction. You weave around people. But now imagine the hallway slowly narrows into a single-file corridor. No one is touching you. No one is pulling you. Yet your freedom collapses anyway. Your choices disappear, not because a force grabbed your shoulders, but because the shape of the space removed the alternatives. That is the closest everyday feeling to strong gravity in relativity. Not a hand pulling, a corridor narrowing, a geometry that decides where motion can go. And near a black hole, the corridor doesn't just narrow, it becomes so strict that some directions of escape are no longer part of the map. So why do visual metaphors mislead? Because almost all of them make gravity into a thing that acts on objects. A rope, a magnet, a vacuum, a pull. But gravity, in Einstein's framework, is the stage itself changing shape. So the straight line your body naturally follows is no longer what you imagined straight to be. This is why strong gravitational fields feel like they violate common sense. Common sense assumes the stage is fixed. But in general relativity, the stage is dynamical. It responds, it curves, it evolves. And when we approach extreme mass densities, we are not approaching more pull. We are approaching a region where the stage bends steeply enough to expose the limits of our language. And this is the first major misunderstanding we must finally set down, gently but firmly. Gravity does not always pull the way we expect. Sometimes gravity is what you call the fact that, left alone, you would follow your natural path, and the natural path is no longer what your instincts consider normal. Now think about this. If you were falling freely toward a black hole, you would not feel a hand dragging you down. You would feel weightless, calm, at least at first. The horror would not begin with a sensation of being pulled. The horror would begin when the geometry changes so sharply across your body that different parts of you are being guided in different directions, tidal forces rising as the field varies from point to point. That is not a monster reaching out. That is space-time becoming too steep to tolerate human-scale structure. And this difference between force and geometry is why black holes are misunderstood from the beginning. Because the moment we use the wrong picture, we start asking the wrong questions. We start imagining a surface where there may be none. We start imagining a wall, a boundary you crash into. We start imagining a place where something happens at a line in space. But then, this creates a bigger problem, because the next idea we meet, the most famous idea in black hole physics, is the event horizon. And the event horizon is exactly where our intuition most desperately wants a surface, even though in the physics, it isn't one. So now we're standing at the edge of a misunderstanding that feels almost unavoidable. If gravity is not a pull, but a geometry, then what exactly is the boundary of no return? Is it a place you hit, a surface you cross, a wall in space, or is it something far quieter? A line drawn not in matter, but in causality itself. Because once we understand what gravity really is, we are ready to face the next unsettling truth. The event horizon is not a surface at all. We keep picturing the event horizon as a thing, a skin, a shell, a black physical edge, like the surface of an ocean, where you cross from air into water. And that picture feels so natural, that it quietly becomes a belief. But the universe does not reward natural pictures, because the event horizon is not a surface you can touch. It is not a wall. It is not a place where space-time ends. It is something far colder than that, a boundary made of causality, a line drawn by what can still affect the outside universe, and what can never do so again. And once we truly accept that, a disturbing truth settles in. The most famous boundary in black hole physics isn't made of matter, it's made of no return in information. NASA often calls the event horizon a black hole's surface, because it behaves like an outer boundary in the simplest explanations. That metaphor is useful, but it is also the seed of a misunderstanding that never stops spreading. Because a surface suggests texture, it suggests impact, it suggests a moment where something happens to you. But the event horizon is not a material surface. It's a geometric boundary in space-time, defined by which paths can still reach the outside universe, and which paths cannot. Outside the horizon, there exist future paths that can carry light and messages outward. Inside the horizon, every future-directed path, every possible forward, leans inward. Not because a force drags everything like a magnet, but because space-time has curved so severely that out is no longer a direction you can choose. This is what it means to be defined by causality. It means that beyond that boundary, no signal you send can ever reach distant space. Not in 1,000,000 years. Not in 1,000,000,000 years. Not even if the universe itself grows old and cold. The outside is simply no longer in your future, and that is why calling it a surface can mislead us. Because a surface is something you can stand on. Causality is something you cannot negotiate with. Here is the strange part. If we could fall toward an event horizon, the moment we reached it would not feel like a collision. It would not feel like passing through a curtain. For the right kind of black hole, especially a supermassive one, the local experience of crossing the horizon can be quiet. This isn't a poetic claim. It's a consequence of Einstein's equivalence principle. In a small enough region of space-time, free fall in a gravitational field can look like weightless motion in empty space. So if we are freely falling, we are not being pressed by gravity. We are being carried along the natural geometry of space-time. And if the horizon is not a physical object, if it is a causal boundary, then there is no requirement for any local shockwave of experience right at the crossing. No flash, no cosmic alarm, no invisible wall. But then, this creates a bigger problem if nothing special happens there. Why does the horizon feel so dramatic from far away? Why do people say time stops? Why do people imagine someone freezing at the edge? Because we're mixing two different realities. The reality of crossing and the reality of watching someone cross. NASA explains the distant view effect in plain language. As something falls toward the event horizon, it appears to slow down more and more until it looks frozen. That isn't because the falling object suddenly hits a physical barrier. It's because the light and signals coming from it have to climb out of an extreme gravitational environment. And as that happens, the light is stretched toward lower frequencies. It becomes redder, less energetic, harder to detect. This is gravitational redshift, one of the clean predictions of general relativity, closely tied to gravitational time dilation. So, from the outside, the story looks like this. The falling object sends signals out, slower and slower. Those signals arrive more delayed. The light becomes increasingly redshifted, fading toward wavelengths we can't practically capture, not because the object refuses to cross, but because the last information we receive is being stretched, delayed, and weakened by the geometry itself. And this is where language begins to distort reality. We say, it never crosses. But what we really mean is, we never receive a final signal that confirms the crossing. That is not a small difference. That difference is the entire story. Because the horizon is not a physical surface that blocks bodies. It's a causal boundary that blocks communication. We confuse those two ideas, and suddenly the universe seems to violate common sense. It doesn't. Our words do. And once our words break, we start inventing false pictures. We imagine a hard edge. We imagine an invisible wall that destroys things. We imagine an instant where the laws of physics suddenly change. But the event horizon is not defined by a local explosion of physics. It's defined by the global structure of space-time, by which futures still connect to the outside universe. That is why treating it as a wall creates confusion, because a wall is something you encounter locally. A causal boundary is something you may cross without noticing, while the rest of the universe quietly loses the ability to hear from you ever again. Imagine this. You're in a building with a heavy door behind you. The door doesn't slam. It doesn't hit you. There is no moment of impact. You simply walk forward, and the door closes silently on its own hinges. Now you can still move. You can still breathe. Nothing about your body changes. But something fundamental has changed anyway. No matter how loudly you shout, no matter how long you wait, your voice will never reach the hallway again. That door is not a wall you crashed into. It's a boundary in communication. That is the closest everyday feeling we can give the event horizon, not a surface, a one-way loss of contact. So what is the event horizon? In the most careful sense, it's the boundary between regions of space-time that can still send signals to the far outside, and regions that cannot. That is why it's defined by causality. Causality is the universe's rulebook for influence. What can affect what? And the event horizon is where influence breaks. Not because signals slow down below the speed of light. Nothing locally outruns light. Nothing needs to. Instead, the geometry shapes the forward directions so completely that even light's future paths no longer include escape. This is also why the horizon is so easy to misunderstand, because we keep mixing two perspectives into one sentence. From far away, we watch an approach that seems endless, light delayed, redshifted, dimmed, the last messages stretched thinner and thinner. From the viewpoint of freefall, the crossing can occur without a special local event at that boundary, consistent with the equivalence principle's core lesson about free fall. Both perspectives can be true, and the universe does not apologize for holding two truths at once. But humans do something dangerous here. We try to compress both into one image, so we say, the horizon is a surface where time stops, and suddenly black holes become fantasy objects, not because the physics is fantasy, because the language is. Now, picture yourself in it. If you were falling freely, you would not feel yourself hit the horizon like a wall. You would not feel a magical boundary under your skin. You would feel your own heartbeat remain normal, your breathing remain real, your sense of now remain intact. But the rest of the universe would begin to lose the ability to receive your now. And that is the emotional truth hidden inside the technical one. A horizon is not a place where physics shatters. It's a place where contact shatters. And once we accept that, we see the deeper pattern. Most black hole myths begin as innocent metaphors. Surface, hole, pull, suction, wall. But black holes punish sloppy metaphors because the real structure is not built from everyday objects. It's built from space-time and causality. And now the misunderstanding tightens. Because if the horizon is not a surface, if it's a causal boundary, then the famous line we repeat, almost like a spell, starts to sound incomplete. Nothing escapes. But what do we really mean by escape? Do we mean a force is trapping things like a cage? Do we mean light is pulled back like a thrown stone? Or do we mean something far stranger, that the geometry of space-time itself removes out from the future? Because once we stop treating the horizon like a wall, we're ready to face the next distortion, one that hardens into myth the moment we say it too casually. Nothing escapes. But that's not the whole story. We've all heard the sentence. It's delivered like a verdict, like the universe closing a door. Nothing escapes a black hole. Not light, not matter, not information. And the sentence is not wrong. But it is incomplete, because the moment we hear it, our minds do something automatic, something human. We picture a force, a pull, a trap, a cosmic hand that grabs anything that comes too close. But black holes don't need a grabbing hand. They don't need suction. They don't need a magical trap at the edge. They only need space-time to be shaped a certain way. And once we understand that shape, the famous sentence changes. It becomes less like a monster story and more like a law of causality. And that is where the real mystery begins. NASA often describes the event horizon as the boundary where the velocity needed to escape exceeds the speed of light. It's a clean phrase, it's memorable, it's also dangerous, because it quietly teaches the wrong mental image. Escape velocity is a Newtonian idea. It belongs to a world where space is a fixed stage, time is universal, and gravity is a force pulling across distance. That world is close enough to our daily lives that the phrase feels like common sense. But the event horizon is not a Newtonian place. It is a relativistic place, where the stage itself bends. So the phrase is not the explanation, it's a translation, a shorthand, a way to point toward the truth without forcing us to think in curved space-time. And that is why the phrase hardens into myth so easily, because we keep the shorthand and forget what it was trying to translate. Here is the problem. When we hear escape velocity exceeds light speed, we imagine light trying to climb out and failing, as if it were a rocket that just wasn't fast enough. But light does not behave like a tired rocket. Locally, right where the light is emitted, nothing strange happens to light. Light still moves at the speed of light in its own local environment, obeying the same speed limit it always obeys. That's not a preference, it's built into relativity. So if light is still doing what light always does, what actually prevents escape? This is where everything changes. A black hole is not best understood as a place where gravity becomes a stronger and stronger pull. It is best understood as a place where space-time becomes so steeply curved that the set of possible future paths narrows and narrows until outward is no longer part of the future at all. MIT's General Relativity course describes an event horizon in exactly this spirit, a surface beyond which communication is not possible. And that word, communication, is the real center of the sentence, nothing escapes. Because escape is not only about speed, it is about causality. It is about whether any signal you emit can still reach the outside universe. A black hole's event horizon is a boundary in space-time. Beyond it, events cannot affect an outside observer. That is why the horizon matters. Not because it's a physical shell, because it's a causal boundary. But then, a new confusion appears. If it's not a wall, and not a pulling trap, why do we keep describing it like a point where you'd need to go faster than light? Because that phrasing is a metaphor for something deeper. Inside the horizon, every future-directed path that light could take, every forward direction available to a light beam, still points inward. Even the paths that look outward in our imagination are no longer outward in the geometry. So to escape, something would have to do more than go fast. It would have to break the structure of cause and effect. It would have to step outside the light cone, the limit that defines what can influence what. And relativity does not allow that. Not for light, not for matter, not for information. So the popular phrase, escape velocity exceeds light speed, is pointing toward a true consequence, but using a picture that belongs to a different universe. And when we keep the picture, we inherit the myth. We start saying, light is pulled back. But in general relativity, the more careful statement is, light is following the straightest paths space-time allows, and those paths no longer include the outside. That is not a trapping force. That is geometry rewriting what forward means. Imagine this. We're in a long hallway with a moving walkway, like an airport. At the start, you can easily walk forward or backward, but the walkway gradually speeds up, faster and faster, always carrying the floor beneath you in one direction. At some point, walking backward is still possible, but it becomes harder, then it becomes exhausting, then it becomes impossible. And finally, there's a line where even if you sprint with everything you have, you cannot make progress against the floor. Now here's the crucial detail. Nothing grabbed you, no hand pulled you. The floor simply changed what motion could accomplish. That's what a black hole does to paths through space-time. And beyond the horizon, it's not that you're weak, it's that out is no longer a destination the future can reach. So what is the phrase, "nothing escapes," actually saying? Without mythology, it is saying that once a world line crosses the horizon, there are no future-directed causal paths from there back out to the exterior region. It is saying that the outside universe is no longer in causal contact with what happens inside, and that immediately clarifies what is and is not forbidden by physics. What is forbidden? From inside the horizon, sending any signal outward to infinity. The outside cannot be influenced from within. What is not forbidden? Emitting light locally while you're still outside the horizon, orbiting a black hole from a safe distance, exactly the way objects orbit any mass. Because outside the horizon, space-time still permits outward paths and stable motion, within limits we'll face soon. This is the part we often miss. A black hole does not erase the laws of physics outside it. Outside the horizon, we can still have orbits, trajectories, and light beams escaping, because the geometry still includes futures that reach far away. So why do people feel so certain that a black hole swallows everything nearby? Because the shorthand becomes a story. Escape velocity exceeds light speed becomes gravity is so strong it pulls even light back. And then that becomes gravity is sucking everything in. And then the black hole becomes a cosmic vacuum cleaner. But that is not what nothing escapes is actually telling us. It's telling us something more precise and more unsettling. There is a region of space-time where the future cannot reconnect to the outside, not because something is chasing you, because the universe's map no longer contains an exit. Now, put yourself there for a second. If you were hovering outside a black hole and you turned on a flashlight, the light beside you would still behave like light. It would still move away from the flashlight at the speed of light, locally, normally, faithfully. But as those photons climb outward through curved space-time, what distant observers receive can be stretched and weakened, tied to gravitational redshift and time dilation near extreme gravity. So we have to hold two truths at once. Locally, nothing breaks. Globally, the geometry changes what reaching the outside even means. And once we understand that, the famous sentence becomes less like a horror line and more like a boundary condition of reality. The myth doesn't start with stupidity, it starts with efficiency. We want to explain a difficult idea quickly, so we use the nearest familiar tool, escape velocity. NASA does it for clarity, because the boundary does behave like a point of no return in simple terms. But if we stop there, we teach the wrong intuition. We teach gravity as a pull strong enough to beat light. And once that picture is in place, everything that follows becomes distorted. We start thinking the black hole is actively dragging the universe inward. We start thinking anything that comes near is doomed. We start thinking the black hole is a kind of cosmic appetite. But nothing escapes is not a statement about appetite. It is a statement about causal structure, and that's why the misunderstanding persists, because force is an easy picture, causality is not. So now we're left with an uncomfortable clarity. Nothing escapes doesn't mean a black hole is pulling harder than light can run. It means the geometry has rewritten the set of possible futures. And once that's true, another myth becomes impossible to ignore. If black holes aren't suction machines, if they don't reach out and grab everything nearby, then why do we keep picturing them as cosmic vacuum cleaners? Why do movies show stars and ships spiraling inward like dust into a drain? Because the next misunderstanding is not about light, it's about motion, orbit, and the quiet, stubborn fact that a black hole's gravity, at a distance, can look exactly like the gravity of an ordinary star with the same mass. The most persistent image is also the most misleading. A black hole is a mouth, a drain, a cosmic vacuum cleaner that sucks the universe like dust off a floor. It's cinematic, it's terrifying, it feels inevitable. But physics is rarely obligated to match what feels inevitable, because the truth is quieter, more embarrassing for our instincts. From far enough away, a black hole does not behave like a cosmic predator. It behaves like mass, plain mass, the same kind of mass that lets planets orbit a star in calm, repeating loops. And once we accept that, the fear doesn't vanish, it changes shape. Because the real danger of a black hole is not that it reaches out to grab everything. The real danger is how easily we mistake drama for mechanics. Here is one of the cleanest truths NASA has ever put into a sentence. Contrary to popular myth, a black hole is not a cosmic vacuum cleaner. And NASA goes further, using an example that quietly dismantles a lifetime of movie. Logic. If our sun was suddenly replaced with a black hole of the same mass, Earth's orbit would be unchanged. Unchanged. We would freeze, yes, because there would be no sunlight, but we would not spiral into darkness like a coin into a drain. Because an orbit is not a struggle against suction. An orbit is a balance between motion and gravity. And outside the black hole, gravity, at a distance, can look exactly like the gravity of any other object with the same mass. This is not a philosophical statement. It is built into the structure of general relativity. In a spherically symmetric vacuum region, the gravitational field outside depends on the total mass, not on whether the mass is a star or a black hole, which means the universe does something deeply unintuitive. It hides the most extreme objects behind perfectly ordinary long-distance behavior. And that's where the misunderstanding begins. Movies teach us a simple story. Get near a black hole, and it pulls harder and harder until you cannot resist. So everything spirals, everything falls, everything is doomed. But that story quietly assumes something that physics does not grant us. It assumes there is no sideways motion. It assumes the universe is willing to forget a conserved quantity that shapes almost everything in the sky. Angular momentum. Angular momentum is why planets don't fall straight into stars. It's why the moon doesn't crash into Earth. It's why galaxies form disks and spirals instead of collapsing into a single silent point. And NASA's own explanations of black holes emphasize that when black holes grow by eating matter, that matter typically settles into a rapidly spinning accretion disk. That disk exists for a reason, not because the black hole is vacuuming, because the infalling gas almost never arrives with perfect aim. It comes with sideways motion, and sideways motion becomes orbit. So the question isn't, why doesn't the black hole swallow everything? The real question is darker. Why does anything fall in at all? If orbit is so natural, that's when the real problem appears. Because a black hole does not pull matter inward through empty space like a hook. In a perfect vacuum, an object placed in orbit around a black hole can orbit indefinitely, just as it can orbit a star. For the object to fall inward, something must remove energy and angular momentum. Something must drain the sideways motion away. And the universe has ways to do that. But they are not suction. They are friction, turbulence, shocks, magnetic stresses, radiation, the messy physics of material interacting with material. That is why accretion disks glow. That is why black holes are often seen through the violence of hot matter outside them, not through the blackness itself. NASA describes accretion disks as the main light source near many black holes, and explains that gas in the disk can become intensely hot, emitting across wavelengths, including X-rays. So the black hole is not vacuuming the room. The room is shredding itself, heating itself, breaking itself, until some of its material finally loses the ability to keep orbiting. That distinction is everything, because it means the black hole is not the active agent in most of the drama. Often, the environment is. The black hole is the boundary condition at the center, cold, silent, waiting. But then, the image in our heads refuses to die, because on screen, spiraling looks like fate. In real astrophysics, spiraling usually means drag. It means matter is colliding, rubbing, exchanging angular momentum, transporting it outward so that some fraction can move inward, and that changes the emotional truth. A black hole is not an appetite that pulls, it is a geometry that allows, and an environment that decides how fast the allowing is turned into reality. Imagine this. We're on a smooth, frozen lake. You slide a puck straight toward the center of the ice. If the ice is perfectly smooth, no cracks, no roughness, the puck keeps its sideways glide. It curves, it misses the center, it circles. Now roughen the ice, add scratches, add friction. Now the puck begins to spiral inward, not because the center sucks, but because the sideways motion is being drained away by contact with the surface. That's what happens to gas near a black hole. The spiral is not proof of suction, it's proof of friction. It's proof that something is stealing orbital energy and angular momentum until orbit can't hold. So why do black holes not automatically consume their surroundings? Because gravity does not cancel motion. Because orbit is not a fragile trick. Orbit is the default behavior of matter moving through space. And at large distances, the gravitational pull of a black hole can be indistinguishable from the pull of any other object with the same mass. That's why NASA can make that unsettling claim about replacing the Sun. Earth would continue its path around the center, roughly 93 million miles, about 150 million kilometers, away, still moving on schedule, still obeying the same large-scale gravitational rules. And to feel what that means, we should translate orbit into something human. Earth moves around the Sun at about 30 kilometers per second, about 19 miles per second. That's roughly 67,000 miles per hour. At that speed, you could circle Earth, about 40,000 kilometers, or 25,000 miles, in around 22 minutes. And we still do not feel that speed. We still live our quiet lives. Because motion is normal in the universe. It's the rest state of a system that has nowhere to dump its angular momentum. So when films show a spaceship getting caught and dragged inward from far away, what they're really showing is a universe that has forgotten what it means for motion to be conserved. And conservation is not optional. It is the spine of celestial mechanics. Now, one direct moment, because it matters. If you were in a stable orbit around a black hole at a safe distance, you would not feel yourself being reeled in like a fish. You would feel nothing. You would feel the same quiet truth astronauts feel while orbiting Earth. Free fall, weightlessness, a kind of eerie peace. The danger would not be that the black hole sucks. The danger would be what happens if you dip too close, or if you enter a region where the environment, gas, dust, radiation, adds drag, stripping away the sideways motion that keeps you safe. That is when spirals appear, not because the black hole becomes a vacuum cleaner, but because orbital support collapses. And this is why movies created the most persistent false image. They blended two different situations into one. The calm, gravitational behavior far away, where orbits can remain stable. The violent environment close in, where matter forms bright accretion disks and can lose angular momentum through interactions, heating into X-rays. On screen, it all becomes one continuous suction story. In reality, the physical story is more subtle and more interesting, because black holes don't need to devour everything to matter. They shape systems through what they allow. They permit stable orbits. They permit violent disks. They permit jets and winds. They permit matter to glow and scream, right up until it crosses the boundary we cannot hear beyond. Even NASA's own outreach material insists on this clarity. From far enough away, a black hole's gravitational effects are just like those of other objects of the same mass. So the mismatch between dramatic visuals and physical reality is not small, it is foundational. It shapes how people misunderstand everything that comes next. Because if we keep imagining black holes as vacuum cleaners, then we keep expecting them to be visible in the wrong way. We keep expecting to see the blackness swallowing the world. But black holes don't announce themselves like that. They're usually revealed by what orbits them, by what heats around them, by what accelerates near them, by what bends and brightens and shifts, without ever showing us the object directly. And now a deeper question replaces the old fear. If black holes aren't cosmic vacuum cleaners, if at a distance they can behave like ordinary mass, then how did we ever become sure they were there? How do we see an object whose defining feature is that it does not let light escape? Because the next truth is the quietest and the most revealing. We learn about black holes by watching everything around them, motion, heat, light, gravity, until the invisible becomes unavoidable. We keep asking the same question, in different disguises. If black holes don't shine, if light can't escape, if the center is, by definition, dark, then how did we ever become so certain they exist? Because certainty usually comes from sight, from photographs, from direct proof. But black holes don't give us that kind of proof. They force a different kind of knowing, a colder kind. We don't see the object. We watch what the object does to everything around it. We watch stars accelerate as if a hidden giant is holding the leash. We watch gas heat until it glows like a wound. We watch light bend into a ring that shouldn't be possible. And slowly, almost reluctantly, we admit it. We're not witnessing a thing. We're witnessing a consequence. That's how black holes enter our world. Not as images, as evidence. NASA says it plainly. When we can't observe something directly, we infer it from its effects, like knowing it's windy because a flag is flapping. That is the honest method behind almost everything we know about black holes. We measure the motion of nearby stars and gas. We measure how fast they swing around an unseen center. We calculate the mass required to produce that motion. And when that mass is too large, too compact, too concentrated to be anything else, the conclusion becomes unavoidable. This is not a romantic guess. It's gravity leaving fingerprints. And those fingerprints show up in a few forms, each one unsettling in a different way. The first kind of proof is motion. At the heart of the Milky Way, about 26,000 light-years from us, a dense cluster of stars moves as if something massive is hidden in the dark. One of the most famous is a star called S2. For decades, astronomers tracked its path with instruments on ESO's Very Large Telescope. They didn't just see a star moving. They saw a star whipping around emptiness, completing a full orbit about every 16 years. And at its closest, approach, S2 comes within less than 20 billion kilometers, about 12 billion miles, of the central object. That's roughly 120 times the distance between Earth and the Sun. To feel that scale, we need to translate it. If the distance between Earth and the Sun were the length of a football field, S2 dives in to within about one football field times 120. Still enormous, still far. And yet, in galactic terms, it's intimate. And at that closest point, the star is moving at almost 3% of the speed of light. That's fast enough to cross the United States, about 4,800 kilometers, roughly 3,000 miles, in about a 20th of a second. A blink is slow compared to that. And yet, even with that speed, S2 doesn't break free and fly away forever. It stays bound. It keeps returning. Because something massive is there. Something with about 4 million times the mass of our Sun. They also measured something even more delicate. The orbit isn't a perfect Newtonian ellipse. It precesses, shifting into a rosette pattern, matching Einstein's general relativity in a regime far more extreme than anything in the solar system. So, this is the first lesson in seeing black holes. We don't see the hidden mass. We see the choreography it forces. The second kind of proof is heat. Motion is persuasive, but heat is theatrical, because black holes often reveal themselves through the violence of matter that hasn't crossed the horizon yet. NASA explains that in some binary systems, matter is pulled from a companion star and forms an accretion disk, a swirling structure where gas collides, heats to millions of degrees, and emits X-rays that telescopes can detect. This is one of the most important clarifications we can make. The black hole is not what shines, the gas shines, the disk shines, the environment shines. The radiation is the sound of matter losing its ability to keep orbiting, and that glow is not gentle. It can be intense enough to be seen across vast stretches of the universe, sometimes outshining the combined starlight of an entire galaxy when a supermassive black hole is actively feeding. So again, we're not seeing the object. We're seeing the bill it forces the universe to pay. The third kind of proof is gravity shaping light itself. And then we arrived at the moment that changed the public imagination forever. April 10th, 2019. The first image of a black hole was released, M87 star, in a galaxy about 55 million light-years away. But we need to say this carefully. That famous orange ring is not a photograph of the black hole as an object. NASA's own description makes this explicit. The black hole is outlined by emission from hot gas swirling around it. The dark center is not the black hole as a surface. It is the shadow, a region where light is bent, captured and removed from our view by the black hole's gravity, leaving a dark central silhouette surrounded by a bright ring. This is where our language almost betrays us again. We call it the first picture of a black hole, but what we truly captured was a boundary phenomenon. Light from hot plasma, curved into a ring-like structure, framing a darkness we can't illuminate. And the technique matters because it explains why this is not ordinary seeing. The Event Horizon Telescope is not a single mirror in space. It is a worldwide network of radio observatories linked together, an Earth-sized virtual telescope built through very long baseline interferometry. We didn't zoom in with a bigger lens. We synchronized the planet. We turned Earth into an instrument, just to glimpse the silhouette of something that cannot shine. And then, in May of 2022, the Event Horizon Telescope revealed an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. The NSF explains the same essential limitation with brutal simplicity. We cannot see the event horizon itself because it cannot emit light, but glowing gas around the black hole reveals a shadow surrounded by a bright ring-like structure. That word, shadow, is the truth. We're seeing the shape of absence. We're seeing the universe draw a circle around something it refuses to reveal directly. Imagine this. It's late at night, and the power goes out in your neighborhood. You can't see the black shape of a house in the darkness, but you can see the outline because streetlights farther away still cast light, and the house blocks it. You don't see the house itself. You see what's missing from the light behind it. That's what the Event Horizon Telescope gave us. Not a portrait of the monster, a silhouette etched by gravity inside a ring of fire. So what does it mean to see a black hole? It means we accept a hierarchy of evidence. Some of it is mechanical and patient, decades of tracking, stellar orbits, watching a star like S2 move as if tethered to a compact mass we cannot otherwise explain. Some of it is violent and immediate, X-ray flares and glowing accretion disks, gas heated to extreme temperatures as it spirals in. And some of it is almost philosophical, a ring of light around a darkness, because gravity itself bends what we can see. But we must hold the boundary between two kinds of knowledge. Direct observation is when the object itself emits or reflects light we capture. Inference is when we observe effects, motion, heat, distortion, and conclude the unseen cause is real. Black hole astronomy is mostly inference, sharpened into confidence by repetition and consistency across many methods. Even the famous images are not direct portraits of the whole. They are reconstructions from radio data, revealing the glow of gas and the shadow that glow frames. And this is why misunderstandings keep returning, because our minds are trained to treat images as final. But black hole images are not final. They are evidence, carefully assembled, pointing toward a reality we cannot witness in the normal human way. Now think about this. When you look at that bright ring, it's tempting to feel like we finally caught the black hole. But what you're really looking at is a limit of human perception turned into a triumph. You're looking at a boundary where the universe says, "You may measure me, but you will not watch me directly." And we only managed it by watching everything around the darkness, until the darkness left no other explanation. So we've learned how to see the invisible, by orbit, by heat, by the bending of light into a ring around a shadow. But there's one consequence of this method that quietly changes everything, because the moment we rely on signals, light, timing, frequency, we are forced to face what gravity does to those signals, not as a metaphor, as a measurable distortion. The closer we get to extreme gravity, the more our measurements disagree about something we assumed was universal: time itself. And that is where the story cracks open. Time feels like the one thing we can trust. It moves forward in our bodies. It moves forward in our memories. It moves forward in the slow erosion of stone. And yet, near a black hole, time becomes unreliable in the most unsettling way. Not because it breaks, not because it shatters into chaos, but because it refuses to be singular. Two observers can look at the same universe and disagree about how much time has passed, and both can be right. That is the quiet horror hidden beneath the famous line we keep repeating: time stops at the edge of a black hole. It doesn't stop, it diverges. NASA describes it plainly. Close to a black hole, time passes more slowly than it does farther away. That statement is accurate, but the way our minds translate it is where the myth is born. We hear more slowly, and we imagine a universal clock being dragged down, like syrup thickening. We imagine time itself crawling. We imagine a traveler reaching a boundary and freezing halfway, between moments. But in relativity, time is not a single river flowing through the cosmos. It's more like countless local streams, each shaped by motion and gravity, each perfectly normal to the people inside it. And the moment we assume there's one master clock that everyone must share, we begin misunderstanding black holes for the rest of our lives. Here's the strange part. Relativity doesn't say time is an illusion. It says time is local. It says every observer carries their own clock, their own proper time, and that clock is real. It's physical. It's measurable. And gravity changes how those clocks compare. Not because gravity reaches into a clock and slows its gears, but because gravity is geometry, and geometry changes what it means for two separated events to be synchronized. We can test this far from black holes, in places that feel completely safe, and we have. In 1976, Gravity Probe A launched a hydrogen mesa atomic clock on a rocket to an altitude of about 10,000 kilometers, about 6,200 miles, and compared it to an identical clock on the ground. The result matched Einstein's predicted gravitational redshift to high precision. This wasn't science fiction. It was a clock, proving that gravity changes the rate at which time accumulates, depending on where you are, and it gets even more intimate than rockets. Every day, our world relies on the same fact. NIST explains that clocks on GPS satellites run faster than clocks on Earth by about 38 microseconds per day once both gravitational and motion effects are accounted for, and that this offset must be corrected for GPS to work properly. 38 microseconds per day sounds tiny, but we should translate it into something we can feel. A microsecond is a millionth of a second, so 38 microseconds is 38 millionths. That's less than the time it takes a camera shutter to blink, and yet, if we ignored it, day after day, those errors would accumulate, quietly bending navigation and timing away from reality. Relativity isn't philosophical decoration, it is engineered into our infrastructure. So when we talk about black holes and time dilation, we're not entering fantasy, we're scaling up a verified phenomenon. Now, here is where the misunderstanding hardens. When people say, time stops, they usually mean this. From far away, an outside observer watching an object fall toward a black hole can see signals become delayed and increasingly difficult to receive, an effect tied to gravitational time dilation and gravitational redshift. This is real, but the leap happens when we turn an observational limitation into a claim about what the falling traveler experiences. Because what the traveler experiences is not frozen time, it's time as usual, inside their own frame, moment by moment, heartbeat by heartbeat. Relativity does not permit a person to feel their own time slow down. Your own second is always 1 second to you. What changes is how your seconds compare to someone else's far away. That's the divergence. And this creates a bigger problem. If time doesn't stop, why do outside observers keep describing a never-ending approach? Because what outside observers receive is not the traveler, it's the traveler's light. And that light has to climb out of a region where gravity reshapes the pathways of signals. NASA describes gravitational redshift as light being shifted to redder wavelengths because of gravity. So as the traveler approaches the black hole, the outgoing signals can be stretched, weakened, and delayed in a way that makes the final approach look endless from afar, not because the traveler is trapped in a frozen moment, but because the outside universe is receiving slower, redder, fainter echoes of the traveler's clock. Eventually, those echoes can slip beyond practical detection. And then the outside observer's story becomes emotionally satisfying. They never cross, but that sentence is a trap, a language trap. It usually means, we never receive a last signal that confirms the crossing. That is not the same thing as, it never happens. This is why the myth survives, because the outside perspective is cinematic. It looks like time itself is failing. But the local perspective is quieter, and human brains are addicted to the dramatic perspective. Imagine this. We're standing on a beach at night, watching a distant lighthouse. The light flashes in a steady rhythm. 1, 2, 3. Now picture that lighthouse slowly moving behind a thick fog bank. The lighthouse doesn't stop flashing. Inside the lighthouse, the mechanism keeps turning like it always has. But to us, the flashes arrive weaker, more delayed, more stretched apart, until we can't see them at all. If we're careless with language, we might say the lighthouse stopped, but it didn't. We just lost access to its rhythm. That's what gravity can do near a black hole. It doesn't have to stop time, it only has to distort our access to someone else's time. So what's the real lesson? Time does not stop. It diverges because relativity does not give us one universal clock. It gives us many clocks, each valid, each local, each shaped by gravity and motion. And this is not just theory. We've measured gravity's influence on time with rockets and atomic clocks. We rely on it every day with satellite navigation. Now, scale that into the environment of a black hole, where gravity can be extreme. NASA states plainly that time dilation becomes significant near massive objects like black holes. But we have to say it with discipline. Time remains locally normal everywhere. A clock you carry does not feel sluggish to you. Your thoughts don't smear. Your body doesn't enter slow motion. What changes is the relationship between your time and the time of someone far away. And this is where the phrase "time stops" does real damage, because it suggests there is a special boundary where physics becomes theatrical, a line where reality freezes. But relativity's most unsettling truth is the opposite. The universe doesn't need a dramatic moment. It can be perfectly continuous, locally calm, while the global comparison between observers becomes increasingly distorted. That is why misunderstanding persists in popular explanations, because we prefer a single story. We want one clock, we want one narrative time. But gravity does not respect narrative convenience, it respects geometry. And geometry allows different observers to build different, consistent accounts of time, without contradiction. Now, picture yourself in it. If you were falling toward a black hole, you would not feel time slowing inside you. You would feel your own time the way you always have, immediate, ordinary, unstoppable. But you would be entering a region where the outside, universe's time could race ahead of you in comparison, where the link between your clock and distant clocks becomes twisted by gravity's shape. And that is the emotional core of gravitational time dilation. Not that time dies, but that time becomes personal, separated, no longer shared the way we assumed it was. And once we accept that time diverges, not stops, we're forced into the next, more uncomfortable question. If our clocks can disagree so profoundly outside the horizon, what happens to description itself after crossing it? What happens to language, measurement, and meaning when the outside universe can no longer receive a signal from within? Because beyond the horizon, the first thing to fail is not physics. It's our ability to speak about what cannot be observed. There is a line in the universe that turns certainty into silence, not a line you can touch, not a wall you can strike, not a glowing border in space. It's a boundary made of causality, a boundary that doesn't just hide what's inside, it prevents the inside from ever speaking back. And that's why this part of the story feels so strange, because the first thing that fails after the horizon is not the math, it's not the laws of physics, it's our vocabulary. Inside, after, now, still. Words that work beautifully in a kitchen, words that work beautifully in a city, start to collapse in the dark geometry of a black hole. And that collapse is exactly where misunderstanding is born. NASA describes the event horizon as a boundary, not a physical surface, containing the matter that makes up the black hole. But the deeper point is more unsettling. MIT's General Relativity course guide states the defining feature in plain, ruthless language. An event horizon is a region from which events cannot communicate with the outside. That is not a dramatic metaphor. That is a statement about what the universe allows. No signal from inside can reach an outside observer. Not light, not radio, not a whispered particle of information. So if we ask, what is it like inside? We immediately hit a wall that isn't made of matter. We hit a wall made of measurement, and physics is built on measurement. So what can physics still describe after the horizon? Surprisingly, quite a lot, but only in a very specific way. General relativity doesn't stop at the horizon. In the mathematics, space-time continues. The equations still allow trajectories, paths through space-time, that cross the horizon smoothly. And the equivalence principle is the quiet reason why. Einstein Online summarizes it clearly. A freely falling observer in a gravitational field does not feel gravity in a small region around them. Locally, the laws of physics look like special relativity, at least for a limited time and region. That sentence is a scalpel, because it cuts through one of the most persistent misconceptions, that the horizon must be a place where something special happens. It doesn't have to be. Locally, in free fall, nothing needs to explode, nothing needs to flash, no alarm has to ring. The horizon is not defined by what you feel, It's defined by what you can send, by what can escape. And when escape becomes impossible, we lose the ability to verify anything from the outside. That's when language begins to fail. NASA is blunt about how we observe black holes at all. We detect them through light emitted by surrounding matter that has not yet crossed the event horizon. That single line tells us something haunting. Everything we see, every glow, every orbit, every flare, comes from matter still outside the boundary. The moment matter crosses the horizon, it can continue on its path, but it can no longer update the universe outside with new information. So the interior becomes a region where physics can still make predictions. But observation becomes one way. We can model, we can calculate, we can infer, but we cannot confirm by looking back out. This is why scientists speak with restraint about interiors. Not because they lack imagination, but because they respect the difference between a solution on paper and a measurement in the sky. And this is where everything changes. Because black holes don't just test gravity, they test what we mean by knowing. Now we reach a problem that sounds technical, but it's actually about the most human thing imaginable: perspective. We all assume we're describing the same reality when we use the same words, but in curved space-time, the coordinates we choose, our labels for time and space, can distort the story. Some coordinate systems make the horizon look like a place where time freezes, or where the equations blow up. And that visual impression is one of the oldest traps in black hole language. A university set of notes on Penrose diagrams and black hole coordinates shows why physicists switch coordinate systems, Eddington Finkelstein for example, to describe what Schwarzschild coordinates make look pathological. This matters for the public misunderstanding, because our brains confuse a coordinate problem with a physical problem. A coordinate singularity is not necessarily a real singularity. It can simply be a bad choice of labels. And when physicists adopted coordinate systems that behave smoothly at the horizon, the story became clearer. The horizon is not a physical tear in reality. It is a causal boundary. But here's the strange part. Even once the math becomes clean, our language still drags behind, because we still talk like the horizon is a place, like there's an inside, the way there's an inside of a room. And there is an inside, yes, but it's an inside defined by what? Futures are possible. That's not how our instincts work. There is another subtle reason language struggles. Some black hole boundaries are not defined by what happens at a point. They are defined by the global structure of space-time, by what can reach faraway regions in the infinite future. A classic review on black hole boundaries points out that event horizons are highly non-local objects, defined in relation to the causal past of future null infinity, the faraway future endpoint of outgoing light. That idea is difficult to speak aloud, but we can feel its meaning. An event horizon is not something you can identify with a local sensor in your hand. It's not like stepping onto a different kind of floor. It's a boundary defined by the total causal map of space-time, by what routes exist for signals to ever escape. So when people ask, where exactly is the horizon? The honest answer is, it depends on the whole space-time story. That is not weakness. That is the nature of the definition. And it's one reason popular explanations keep drifting into fantasy, because fantasy loves sharp surfaces. Physics sometimes gives us boundaries that are real, but not tactile. Imagine this. You're in a long hallway with doors behind you. Every few steps a door locks. At first, it's not frightening. You can still walk forward and feel normal. You can still breathe. You can still speak. But then you look back and you realize something has changed. Not in your body, not in the air, but in your options. At some point, there's a door that locks in a final way. From that moment onward, no matter how fast you run, no matter how hard you push, you cannot return to the open world behind you. Nothing dramatic happened to your skin. Nothing changed in the texture of the floor, but your future became one-directional. That's closer to what an event horizon is. A boundary where your set of possible futures collapses into a narrower shape. A boundary where escape stops being a physical struggle and becomes a logical impossibility. So what can physics still describe after horizon crossing? It can describe trajectories through space-time. It can describe what happens locally to an infalling observer for a time. It can describe how causal structure changes, how light cones tip, how futures become constrained. It can even describe the relationship between different coordinate systems and why some descriptions mislead. But physics cannot do something that many people quietly demand. It cannot give us a direct interior report returned to the outside, because the defining feature of the horizon is that interior events cannot communicate outward. And this is where scientists become careful, almost ritualistically careful. Not because they're afraid of wonder, but because they know the difference between we have a consistent theory that extends inward, and we have observational access to verify what happens inward. NASA's description of how we observe black holes keeps us honest. We're observing the environment outside the horizon, not the interior. So when scientists say, we don't know, it is not a retreat. It's rigor. It's the discipline of refusing to pretend that a boundary of causality is merely a boundary of imagination. Now, put yourself there for a second. If you cross the horizon in free fall around a sufficiently massive black hole, the laws of physics in your immediate vicinity could remain locally ordinary for some time, because locally free fall erases the feeling of gravity in small regions. But something would already be lost forever: your ability to prove it to the universe outside. Your story would continue, but the universe would stop receiving updates from your timeline, and that is the deepest reason language fails, because language evolved for shared realities, shared clocks, shared signals, shared confirmation. A black hole. Interior is where confirmation becomes one way. So we can describe the horizon as a boundary, not a surface. We can describe it as a limit on communication. We can describe why coordinate systems can mislead us into thinking something breaks there. But beyond that boundary, the most dangerous mistake is not mathematical, it's linguistic. Because the moment we say inside, we are tempted to picture a place with objects the way our world has objects. And that temptation leads us straight toward the most misunderstood word in black hole science. A word that sounds like a thing, but is often a sign that our theory has reached its limit. The word is singularity. We keep saying it like it's a thing, a singularity, a dark pebble at the center, a cosmic needlepoint, a final physical place where everything ends. But that word is a trap, because in physics, when a calculation produces an infinity, it isn't always revealing nature. Sometimes it's revealing the edge of our language, the edge of our theory, and black holes are where that edge becomes impossible to ignore. So if we want to stop misunderstanding black holes, we have to stop picturing the singularity as an object, because a singularity is not an object, it's a warning. NASA's black hole anatomy description is clear about what general relativity predicts. At the center, a point where matter is crushed to infinite density. But NASA adds something equally important and far more honest. They explicitly say astronomers don't know whether the singularity is a physical structure or a purely mathematical one, and that the prediction may signal the limits of relativity, where quantum effects become important. That single sentence is the entire story, because it tells us the singularity isn't a trophy we found. It's a sign we've reached the boundary of what our current tools can describe. To understand what a singularity is, we have to strip away the imagery first. The Einstein Online Explainer, written by working relativists, frames it in a way that sounds almost brutal. A space-time singularity is where a freely falling particle's path simply ends. The geodesic cannot be extended any further. This is called geodesic incompleteness. That is not a description of a little ball of matter. It's a description of a failure in the space-time map, a place where the theory stops being able to continue the story of motion. And that's why singularities can be so misunderstood, because our instincts here center and imagine a physical core. But the mathematical definition many physicists rely on is closer to, here is where the space-time description becomes incomplete. So the singularity is not necessarily something, it can be the boundary of the model. Now we face the most seductive word in all of this: infinite. NASA's older educational material says the singularity is vanishingly small, with essentially an infinite density, and adds that it's likely the laws of physics break down there. That is exactly the point. Infinity is not a comfortable destination in science. It's usually a flare shot into the sky by a theory that has run out of jurisdiction, because real measurements never return infinity. Our instruments return numbers. Our universe returns finite signals. And when a theory returns infinite density, the most responsible interpretation is not, "we found infinity." It's, "our description is incomplete under these conditions." This is where the story cracks open, because black holes tempt us to confuse a mathematical extreme with a physical object. But those are not the same. A map can contain a blank space without the Earth containing a void, and general relativity, magnificent as it is, does not include quantum physics. NASA is direct. The singularity prediction may be where quantum effects become important in a more complete description of gravity. So if we treat the singularity like a confirmed thing, we are doing something very human. We are turning an unknown into an image we can hold, and that image becomes a myth. We need to be precise about what breakdown means. General relativity is one of the most successful theories ever written. It predicts gravitational lensing, time dilation, and black hole horizons with extraordinary accuracy. But a theory can be stunningly correct across vast ranges and still fail in extreme corners. A singularity is one of those corners, and the difference matters. Physical reality is what the universe does. Predictive failure is what our equations do when they can't continue. Einstein Online's framing, geodesics that cannot be extended, describes a limit of description, not a camera snapshot of a physical dot, and modern scholarship keeps sharpening that point. A 2022 review in Philosophical Transactions of the Royal Society stresses that common interpretations of singularity theorems can be oversimplified, and it carefully distinguishes what the theorems actually establish from the stronger claims people attach to them. The theorems are powerful, but they are not license for fantasy. They tell us something like, under reasonable conditions, classical spacetime cannot remain complete. They do not hand us a physical object we can place on a table. So why do singularities feel so real in public imagination? Because the word behaves like a noun. A singularity sounds like a thing you could point to, and the culture of pop science often treats it that way. The core, the point, the ultimate object. But NASA's own wording quietly resists that temptation. It says we don't know whether it's physical or mathematical. That is not evasive. That is scientific discipline. A singularity is a placeholder in this sense. It marks where our current theory predicts its own failure. It is a signpost reading, "Beyond this point, new physics is required." And the moment we mistake a signpost for a destination, the misunderstanding begins to multiply. Imagine this. We're using a navigation app while driving through a city we've never seen. It works perfectly for hours, turn by turn, street by street. Then suddenly, we reach a region where the map data is missing. The screen doesn't show the roads ahead, not because the roads don't exist, not because reality ends, but because the map is incomplete. If we're careless, we might say, "There's nothing there." But what we really mean is, our tool cannot describe that region. That is the singularity in a black hole story. General relativity is the map. It's astonishingly accurate, until the conditions become so extreme that the map stops being trustworthy. So what does a singularity represent? In the strict language of relativity, it's often treated as a boundary where space-time is incomplete, where the theory cannot extend the paths of particles and light any further. In the popular language of infinite density, it's the place where our classical description produces infinities, and NASA emphasizes that this may signal the limits of relativity, pointing toward the need for quantum physics in a fuller theory of gravity. That's the calm truth. Singularities are not confirmed objects. They are where our best classical theory stops being enough. Now, one direct moment, because this is where people quietly fear the wrong thing. If you imagine the singularity as a literal object, an infinitely dense thing, you will inevitably imagine physics, becoming theatrical and monstrous in a way we can narrate with certainty. But the more accurate, more honest view is harder. We cannot yet describe the deepest interior with complete confidence, because the boundary of communication cuts us off, and our theory signals its own limits. That we don't know is not weakness, it's rigor. It's the refusal to turn an equation's breakdown into a myth with a face. And once we understand singularities as warnings, not objects, another danger appears. Because black holes have another idea attached to them, an idea that makes headlines, an idea that sounds simple, almost comforting, that black holes might not be eternal, that they might evaporate. And the moment we say the name tied to that claim, Stephen Hawking, we enter a territory where subtle mathematics becomes a single sentence in a news feed. And that is where misunderstanding becomes contagious. There's a phrase that keeps returning like a ghost. Black holes aren't black. It's said with the confidence of a fact we can point to, as if someone has seen the glow, as if a telescope has caught the last breath of a dying hole. But what we're really repeating is something stranger than an image. We're repeating an equation, a prediction, a whisper from the border between two great theories that do not fully trust each other. And the danger begins the moment that whisper becomes a headline, because Hawking radiation is real physics, but the way we talk about it is often a beautiful distortion. And that distortion has consequences, not because it makes us less impressed, but because it makes us misunderstand what science actually is. A method, a set of limits, a language that becomes more careful, not more dramatic, as it gets closer to the edge. In the 1970s, Stephen Hawking did something that still feels almost impossible. He took the mathematics of quantum, physics, fields, fluctuations, uncertainty, and placed it against the mathematics of curved space-time, the domain of Einstein, the geometry of gravity. And from that collision, a new result emerged. A black hole should emit radiation, not because it has a furnace inside, not because light leaks, but because, in quantum physics, empty space is never truly empty. Even a perfect vacuum is not a silent void. It's a restless microscopic turbulence, fields jittering with uncertainty, always, and near an event horizon, that restlessness meets a boundary that splits the universe into two different causal fates. One side can still send signals outward, the other side cannot. That divide changes what empty means. That's the unsettling heart of Hawking's idea. We need to be careful here, because the most common explanation is also the most misleading. You've heard the story. Particle pairs appear near the horizon. One falls in, one escapes. That picture can be a useful metaphor, but it's not the deepest explanation. The deeper explanation is colder and stranger. In curved space-time, different observers don't agree on what counts as a particle. The vacuum itself becomes observer-dependent, and a horizon changes the bookkeeping of quantum fields. What looks like emptiness to one observer becomes a thermal glow to another. So the black hole behaves like it has a temperature, not a temperature you could feel with your skin, not a warmth you could stand near. For a black hole the mass of our sun, that temperature is unimaginably tiny, far below a single degree above absolute zero, and that detail changes everything. Because once we say radiation, the human mind hears light. Once we say temperature, the human mind hears heat. But this is not a campfire in space. This is a mathematical glow so faint that the universe itself drowns it out. Space is not truly cold in the way we imagine. Even far from stars, the universe is filled with a relic warmth, the cosmic microwave background, a leftover afterglow from the early universe. It's everywhere, and it sits at about 2.7 kelvins, about 2.7 degrees above absolute zero. Now hold on to that, because for most real black holes, the ones formed from collapsed stars, the Hawking temperature is below that background, which means, in practice, they don't spend this era of cosmic history evaporating, they spend it absorbing. The universe is still warmer than they are. So even if Hawking radiation exists, the net effect for astrophysical black holes today is not a dramatic shrinking on a human timescale. It's almost the opposite. The cosmos feeds them more than they bleed. And this is where the headline begins to crack, because the popular story implies urgency. The real physics implies patience. Hawking radiation is not just hard to detect. For astrophysical black holes, it is absurdly hard. The predicted signal is so small that even our best instruments are not simply not good enough. They're trapped in a deeper problem. The signal is buried beneath stronger sources of radiation everywhere we look. This isn't a matter of building a slightly better telescope. It's a matter of separating an unimaginably faint quantum whisper from a universe that is loudly alive. That's why, even decades after Hawking's prediction, we have not directly detected Hawking radiation from an astrophysical black hole. And that absence is not a failure. It's a measurement of scale. It's the universe reminding us that some truths are real and still inaccessible. Now the part headlines love, black holes evaporate. Yes, according to the theory they do, but not the black holes we film in our imagination, not the ones swallowing stars in Hollywood storms. A stellar mass black hole, something like 10 times the sun's mass, would take on the order of 10 to the power of 67 years to evaporate. 10 to the 67th years. And we need to translate that, because the number by itself means nothing to human nerves. The universe is about 13.8 billion years old, roughly 14 billion years. So a 10 solar mass black hole's evaporation time isn't just longer than the age of the universe. It's longer by a factor so extreme that language itself starts to break down. Imagine writing the age of the universe on a piece of paper. Now, imagine stacking pages until the pile reaches the moon, about 384,000 kilometers, about 239,000 miles. Now imagine doing that again, and again, and again, until the repetition becomes its own kind of silence. And even that still doesn't give your mind a real grip on 10 to the 65 years. That's the timescale Hawking gave us. And the timescale is the point, because it tells us what kind of claim this is. Not a claim about tomorrow, not even a claim about human civilization, a claim about the far future of physics itself. Picture this, a mountain of ice in the dead of night. The air is so cold that nothing melts. But, molecule by molecule, the ice still disappears through sublimation, a slow escape, a steady vanishing that your eyes will never catch in real time. That's closer to Hawking radiation than the word evaporation suggests. Not a dramatic boil, a patient leaking of energy, so slow that the universe could live entire eras and never notice the difference. And this is why headlines are dangerous, because the word evaporation carries the wrong emotional speed. It sounds like action. The truth is, it's almost stillness. When physicists talk about a black hole losing mass, they're speaking in the language of energy accounting. Radiation carries energy away. Energy and mass are tied together, so the black hole's mass decreases. But it decreases meaningfully only when the black hole is small enough that its temperature rises enough to outshine its environment. Smaller black holes radiate more strongly. Larger black holes radiate more weakly. That relationship is one of the most counterintuitive pieces of modern physics, and it's exactly why we misunderstand it so easily. Because our instincts are built for fires and furnaces. In our world, bigger things tend to stay hot longer. But black holes are not objects in the usual sense. They are regions of space-time with horizons, and the temperature is not a substance inside them. It's a property of that horizon in quantum field theory. So we're not dealing with intuition, we're dealing with translation. Every few years, a wave of articles rises. Scientists observed Hawking radiation, and it's always worth reading carefully because often something real is happening. There have been experiments in laboratories that create analog horizons, systems in fluids, optical setups, or ultra-cold gases, where waves experience a one-way boundary similar to an event horizon. These experiments can mimic aspects of Hawking's mathematics. They can test pieces of the logic. But that is not the same as detecting Hawking radiation from an actual black hole in space. The analogy can be meaningful and still not be the thing itself. This is the subtlety that headlines flatten, because headlines need a single sentence. Physics needs an entire paragraph, and sometimes an entire century. So where would we even look? If we want Hawking radiation strong enough to matter, we need black holes that are much smaller than stellar remnants. That raises a serious scientific path. Primordial black holes, hypothetical black holes that could have formed in the early universe under extreme conditions. If any of them exist at the right masses, some could be finishing their lives now, ending in bursts of high-energy particles. Scientists have searched for those signatures in gamma rays. For example, analyses using data from instruments like the Fermi Gamma Ray Space Telescope have placed constraints on these events, and the absence of definitive detections tightens the limits on how many such evaporating black holes could exist nearby. Notice what that means. Even here, at the best possible target, we're still dealing with constraints, limits, and careful phrasing. Not certainty, not spectacle. Science at the edge is usually not a triumphant announcement. It's a narrowing of possibilities, a slow tightening of the net. So let's separate what's solid from what's sensational. Hawking radiation is a serious theoretical result. It emerges from combining quantum field theory with curved space-time. It implies black holes have a temperature and can, in principle, lose mass. But it has not been directly observed from astrophysical black holes because the predicted signal is extraordinarily small and overwhelmed by other cosmic backgrounds. And for stellar mass and supermassive black holes, the evaporation times are so long, far beyond the current age of the universe, that the process is not a practical drama in our cosmic era. Now here's the dangerous exaggeration, that Hawking radiation means black holes are slowly dissolving before our eyes. They are not in any meaningful sense. The honest version is more haunting. Hawking radiation suggests that even the darkest objects in the universe are not perfectly eternal, that the cosmos may have no true locks, only doors that take unimaginable time to open. And this is where we return to something intimate. Because the real story of Hawking radiation isn't actually about black holes shrinking. It's about us learning to live with a truth that doesn't come with a picture. You can't watch a stellar black hole evaporate, not with your lifetime, not with your species' lifetime. So you are forced into a different relationship with knowledge. You are forced to accept that some ideas become credible, not because we saw them, but because the structure of the universe leaves no easy alternative. And that is unsettling in a quiet way. It means the universe can be understood without being directly witnessed. And that realization is both powerful and dangerous. because it makes language even more important. It makes precision sacred. Here's where the story cracks open. Hawking radiation is often presented as a clean, finished idea, but it touches one of the deepest unresolved tensions in physics. What happens to information in a black hole? If a black hole radiates away and disappears, what happens to the information about what fell in? That question triggered decades of debate, careful arguments, and new ideas about quantum theory and gravity. And it's not a question we can answer with a catchy sentence. It's a question that exposes the limits of our models. And that's the real danger of headlines. They make mysteries sound like solved problems. They trade the careful edge of science for the comfort of closure. But the universe does not give closure cheaply. So Hawking radiation is not a myth. It's not a fantasy. It is a mathematically grounded prediction that has reshaped how physicists think about horizons, temperature, and the fate of black holes. But it is also a perfect example of how we keep misunderstanding black holes. We take a subtle theoretical statement, we compress it into a dramatic sentence, and then we mistake that sentence for reality. And once that happens, we stop listening to the real lesson. Because the real lesson is not black holes evaporate. The real lesson is this: our minds crave stories that move at human speed. But black holes do not live at human speed. They live at the speed of space-time itself. And when we force them into our narrative instincts, we don't just simplify, we distort. And that raises a more uncomfortable question, one that has less to do with black holes and more to do with us. Why do we keep doing this? Why do we keep turning careful science into comforting images? Why do we keep getting these objects wrong, even as our data gets better? Because the misunderstanding isn't only in the sky, it's in the way the human brain tries to make the universe feel familiar. We live inside pictures, not because the universe is simple, but because our brains demand it. We take something that doesn't belong to our senses, curved space-time, collapsed stars, horizons built from causality, and we force it into the oldest human language we have, a story with characters, a scene with a center, a villain with a pull, and black holes. They punish that habit, because they are not things we can hold in the mind the way we hold a mountain, or a storm, or an ocean. They are relationships, between mass and geometry, between time and distance, between what can happen and what can never be seen. But then we do what humans always do. We flatten them into a single image, a dark mouth, a cosmic vacuum, a hole in space. And once that image takes root, it becomes harder to remove than any mistake in the math, because it feels true, and that's the real problem. Not that black holes are confusing, but that they are too easy to misunderstand. Imagine you're trying to explain a symphony to someone who has never heard sound, not someone who doesn't like music, someone who has never experienced vibration as meaning. So you hand them a sheet of paper, you draw symbols, you point to the notes, you describe rhythm, and you hope, quietly, desperately, that the page will somehow become the music. But the page is not the music. It's a code, it's a translation, and it only works if the person reading it already lives in a world where sound exists. Black holes are like that. We're trying to translate something real into a human sense system that was built for walking, grabbing, surviving, and reading faces in firelight. And that mismatch is why we keep getting them wrong. We are animals from the surface of one planet. We grew up under one kind of gravity, weak, consistent, and familiar. To us, gravity feels like a pull, like a hand, like an invisible rope tied to the ground. That intuition is useful for survival, but it quietly trains us to think the universe is built out of forces that behave like hands. And black holes, more than almost anything else in physics, expose that as a comforting illusion. Even in modern explanations, we often reach for the same old verbs. It pulls, it sucks, it drags. Those words are not just imperfect, they are dangerous, because they smuggle in a picture of intent, a black hole as a predator, a hungry object, a cosmic mouth. NASA has to say this plainly because the myth is so persistent. Black holes are not cosmic vacuum cleaners, and from far enough away their gravity is the same as any other object with the same mass. And yet the vacuum cleaner image survives. Not because people are irrational, but because our minds are built to trust stories more than equations. There is a reason the rubber sheet image of gravity refuses to die. It is visually beautiful, a heavy ball sinking into a stretched fabric, pulling smaller marbles inward. It gives our eyes something to hold, but it also quietly teaches something false, because space-time is not a fabric sitting inside a larger space, and gravity is not a dip that objects fall into like a drain. The metaphor works until it becomes our belief. And once we believe the metaphor, we start treating black holes as literal holes, as if space is a surface that can tear, as if the universe has a flaw, as if the center is a place you can point to like a dot on a map. But the more faithful picture is stranger. Gravity is not a pulling force in the way our muscles pull. It is the shape of space-time itself, and our senses were never designed to feel shape in 4 dimensions. So our minds do what they always do with the unseeable. They invent a picture, and then they trust it more than the truth. Scientists don't speak the way headlines speak. Scientists speak in careful gradients, in uncertainties, in confidence intervals, in conditions, and they do it for a reason, because nature does not reward certainty. But human language does. Human language rewards the clean sentence, the final answer, the dramatic claim. So the moment a black hole story leaves the careful world of research and enters the world of human attention, it is squeezed. Complexity is trimmed. Caveats are shaved off. The uncomfortable we don't know is treated like weakness, and the result is a story that sounds powerful, but becomes fragile. Research on science news shows that the pressure for newsworthy storytelling can distort which findings get attention and how confidently they're framed. And it's not just journalists. Even press releases, the official bridge between research and the public, can be a major source of exaggeration and missing caveats, and those distortions can flow downstream into media coverage. So what happens with black holes, objects already designed to break intuition, is predictable. The story becomes sharper, simpler, more absolute. Nothing escapes. Time stops. Everything is crushed. And those phrases are not entirely wrong, but they are incomplete in ways that matter. Here's the strange part. Even when we hear a correction, we often keep the myth. We store the truth as a footnote, but we keep the image as the main memory. Because myths are efficient, they compress reality into something we can carry. A black hole becomes a place where gravity is infinite, a region where time freezes, a monster that eats stars. These phrases are easy to repeat, easy to animate, easy to fear. NASA's own educational material has to clarify this exact trap. It's misleading to say time stands still at a black hole, because locally the falling observer doesn't experience their own clock stopping. The freezing is tied to what a distant observer can see. That difference between what's experienced and what's observed doesn't fit well in a single dramatic sentence, so we abandon it, and the myth wins. There is another quiet bias at work. We think that if we can't picture it, we don't understand it. But in modern physics, the deepest truths often arrive without a picture. They arrive as structure, as consistency, as prediction. Black holes became credible not because someone drew them beautifully, but because their consequences began appearing in data. The trouble is, the public relationship with science is often built through images first. And images don't naturally carry conditional statements. An image is not good at saying, this is inferred, this is a boundary of causality, this is what a distant observer can or cannot receive. An image is good at saying, this is a thing, So the moment we see a black hole through an illustration, we treat the illustration as a photograph, and then the misconceptions become emotionally anchored. They stop being ideas, they become memories. A black hole story competes for attention against everything else in modern life. And attention is not patient. It doesn't reward slow accuracy. It rewards shock. It rewards the clean sentence that lands like a hammer. But black holes don't behave like hammers. They behave like geometry. So the story is often forced to become more violent than the physics, more final than the evidence. And we should say this carefully, because exaggeration is not always a simple villain. Some research suggests journalists sometimes understate scientific claims rather than overstate them, depending on context and norms. The real pattern is messier, but black holes are especially vulnerable to distortion because the accurate truth is already counterintuitive. So even small shifts in wording can create a completely different mental model. A single word, suck, can reshape the whole picture. A single phrase, time stops, can fossilize into a belief that feels scientific, even when it isn't framed correctly. And once that belief spreads, it becomes cultural, it becomes cinematic, it becomes the default, and this is where it gets personal. Because this isn't only about the media, it's about us. Right now, even as we listen, our minds want to simplify. You can feel it. Your brain wants a shape, a surface, a center you can point to, and if we don't get one, we feel uneasy, as if the explanation failed. But the discomfort is not failure, it's accuracy. Black holes do not give us the kind of understanding we evolved to want. They give us a different kind, a colder kind, a truer kind, one built not from images, but from limits, from what can be measured, from what can be inferred, from what must remain unsaid. We have more evidence than ever. We have precise measurements of stars orbiting invisible masses. We have X-ray telescopes watching hot gas swirl. We have international collaborations building images from signals that cross the galaxy. And yet, the old misunderstandings persist, because improved data doesn't automatically replace old mental models. A better measurement doesn't erase a better story. It has to compete with it. And stories have an unfair advantage. They fit inside us. They compress the universe into something human-sized. But black holes are not human-sized. They are the universe refusing to be reduced. And this is why black holes are not just objects in space. They are stress tests for the way human minds relate to truth. So maybe the question isn't, why do people get black holes wrong? Maybe the deeper question is, why do we demand that the universe makes sense to the kind of mind we happen to evolve with? Why do we treat intuition as a judge instead of treating it as a limited tool? Because when black holes expose the failure of our mental pictures, they aren't mocking us. They are teaching us something, not about darkness, not about monsters, but about restraint, about the courage to say, we can know, without being able to imagine. And once we accept that, another kind of understanding begins, not loud, not cinematic, not fueled by conquest, quiet, human. A recognition that our greatest scientific achievements often come with a strange humility attached. And that humility might be the most important thing black holes have ever given us. Because in the end, they don't just bend light, they bend the way we think. And what comes next is even calmer and even harder, what black holes quietly teach us about our own limits. There are nights when the universe feels gentle. The stars don't shout, they don't explain themselves, they just hang there, cold and precise, like facts that don't need our permission. And yet, in that calm sky, we carry a strange belief that if we look long enough, if we build the right telescope, if we gather enough data, the universe will eventually become intuitive. that one day black holes will feel as familiar as gravity under our feet. But black holes do something disturbing. They remind us that nature is not obligated to fit inside the shape of a human mind. Not even a brilliant one, not even a trained one. They are not only objects out there, they are mirrors. And when we look into them, we don't just see darkness. We see the edges of our own understanding. We often say we understand black holes. We know they form when massive stars collapse. We know their gravity can shape the motion of stars and gas. We know their presence can be inferred with staggering precision. We can predict orbits. We can measure light bending around invisible mass. We can watch hot matter spiral into something we cannot see. That's knowledge. But understanding is different. Understanding is what happens when a fact becomes part of your inner world, when you can feel its logic without forcing it, when it stops being a sentence you repeat and becomes something your mind can inhabit. And this is where black holes become unbearable, because they are a place where knowledge keeps increasing, while understanding refuses to keep up. We can become more accurate and still feel more lost. And that tension between precision and intuition is not a weakness of science. It is one of its most honest revelations. Our intuition is not a map of reality. It is a survival tool. It was shaped for things that fall at familiar speeds, across familiar distances, inside familiar times. It was shaped for rain and fire and predators and hunger. It was not shaped for warped space-time, not shaped for horizons defined by causality, not shaped for a place where before and after stop behaving the way we expect. So when we try to picture black holes, we instinctively turn them into something our intuition can digest. A tunnel, a mouth, a hole in a fabric. And that's why misunderstanding is so persistent, because the mind doesn't want the truth. The mind wants a picture. But black holes are not a picture. They're a relationship between geometry and limits. They are a place where our oldest mental habits, force, pull, surface, center, begin to fracture. And that fracture feels like confusion. But it's something else. It's the mind noticing its own boundary. Imagine you're holding a glass of water. You tilt it slightly, and the water leans with the motion. A little more tilt, and it slides. A little more, and it spills, predictably, into the world. Now imagine trying to explain that water to someone who has never experienced gravity. They might understand the words, they might memorize the rules, but the felt truth, the quiet certainty in your body that water will fall, would be missing. Black holes are like that. We can learn the rules, we can repeat the language, we can even make correct predictions, but our bodies cannot feel curved space-time. Our eyes cannot see causality as a boundary. So the mind, desperate to close the gap, fills the space with metaphor, and metaphor becomes belief. That is how a scientific truth turns into a cultural myth, not through stupidity, through human nature. There's a phrase scientists use that the public often misunderstands. We don't know. People hear it like defeat, like surrender. But in science, we don't know is not weakness. It's discipline. It's the refusal to build a story where evidence ends. It's the humility to admit where measurement stops and imagination begins. Black holes force this honesty because they sit at the edge of what can be tested. We infer them through their effects. We measure their influence. We assemble their presence from what they do to light and matter and time. But there are questions we cannot answer in the way we wish we could. Not yet, and maybe, in some cases, not ever in a human way. So black holes teach us a different kind of courage, the courage to live with incomplete pictures, without turning them into fantasies, the courage to let reality remain strange. Mystery is not a failure. Mystery is what happens when we are touching something real that exceeds us. Myth is what happens when we refuse to tolerate that discomfort. Myth replaces the unknown with a story that feels complete. And black holes are one of the places where myth grows fastest, because the truth is subtle, the truth is careful. The truth requires us to say sentences like, from far away, it looks like this, but locally, it feels like this. The truth requires perspective, and humans hate perspective when it slows down the story. So the myth becomes louder. Time stops. Everything is crushed. It swallows galaxies. But the universe is rarely that theatrical. It is colder than our drama, more patient than our fear. And black holes remind us that our emotional appetite for spectacle is not a reliable guide to reality. When we say we want to understand black holes, what we often mean is we want them to fit. We want them to sit inside our intuition like a stone sits in a hand. But black holes don't fit. They don't agree to become simple. They don't slow down so our minds can catch up. They force us to upgrade the meaning of the word understand. Understanding, in this deeper sense, is not about comfort. It's about coherence. It's about building a model that survives contact with the universe, even if it doesn't satisfy our imagination, even if it refuses to become a picture. This is the quiet trade that modern science makes. We give up the demand for intuitive certainty, and in return, we gain the ability to speak truthfully about things we cannot directly touch. That trade is not glamorous, but it is one of the most profound achievements of our species. Here's the uncomfortable truth we rarely say out loud. The universe is under no obligation to make sense to us. Not to our eyes, not to our language, not to the stories we grew up with. A black hole does not care that we want a surface to imagine. It does not care that we want a center that behaves like a location on a map. It does not care that we want now to be universal. Nature does what it does, and our job is not to force it into human-scale thinking. Our job is to build tools, mathematical, experimental, observational, that let us approach it honestly, even if the price is discomfort, even if the price is humility. That is what black holes demand from us. Not worship, not fear, restraint. And if you listen carefully, you can feel it. That moment when the mind stops trying to win and starts trying to see. You don't need to imagine a black hole perfectly. You don't need to turn it into a monster or a mouth or a tunnel. You only need to accept something calmer, that the universe is larger than the part of it we can visualize. And that is not a tragedy. It's a kind of liberation. Because once we stop demanding that everything be intuitive, we become capable of a deeper relationship with reality, a relationship built on respect, on patience, on the quiet strength of saying, we know this much, and we will not pretend we know more. There's a myth about science that even educated people sometimes carry, that science is conquest, that it is the mind overpowering mystery, that it is the universe being forced to confess. But the real story is quieter. Science advances not just by bold claims, but by careful limits, by noticing where language misleads, by refusing the convenient metaphor, by separating what we can measure from what we only want to believe. Black holes magnify that lesson, because they are where bad language becomes dangerous, where a single oversimplified sentence can produce decades of misunderstanding, where one metaphor can replace reality in the public imagination. So the mature approach to black holes is not louder, it is slower, more precise, more respectful, because when the universe is strange, the worst thing we can do is rush. In the end, black holes might be teaching us something more human than scientific. They remind us that knowledge is not the same as mastery, that seeing is not the same as understanding, that mystery is not a defect in the world. Sometimes mystery is the world being bigger than our minds, and maybe that is the true reason we misunderstand black holes so often. Not because they are too dark, but because they reveal something we rarely want to face: how much of reality exists beyond human-scale thinking. We used to look at the night sky and think it was a ceiling. Then we learned it was depth. We used to think gravity was a pull. Then we learned it was shape. We used to believe that if we couldn't picture something, it wasn't real. And then black holes arrived and refused to fit, not as monsters, not as cosmic mouths, but as silent proof that the universe is not built for our comfort, only for its own truth. And the quietest, most human conclusion is this: we don't misunderstand black holes because we are foolish. We misunderstand them because we are human. And sometimes the most honest form of understanding is the willingness to stop forcing the universe to feel familiar and to let it remain calmly, beautifully beyond us.